A voltage regulator is a crucial component in electronics, ensuring that devices receive a stable voltage despite fluctuations in input power. Imagine it as a traffic cop for electricity, directing the flow to keep everything running smoothly. Without it, devices could face overvoltage, leading to damage, or undervoltage, causing them to malfunction. There are different types of voltage regulators, like linear and switching types. Linear regulators are simple and provide clean output, but they can waste energy as heat. On the other hand, switching regulators are more efficient, converting excess voltage into usable power. In essence, voltage regulators are the unsung heroes of our gadgets, maintaining the balance that keeps our technology alive and kicking. A voltage regulator is an electronic device or circuit that maintains a constant output voltage, regardless of changes in input voltage or load conditions. It ensures that electronic devices and circuits receive a stable voltage, which is crucial for their proper functioning and longevity. There are two main types of voltage regulators. Linear voltage regulators are simple and inexpensive, provide a constant output by dissipating excess power as heat, and are less efficient, especially when the difference between input and output voltage is large. Common examples include the 78XX series, such as the 7805 for 5V output, and the LM317. Switching voltage regulators are more complex but much more efficient, using inductors, capacitors, and switches, usually transistors, to regulate voltage through high-frequency switching. Types include buck converter, which steps down voltage, boost converter, which steps up voltage, and buck boost converter, which can step up or step down voltage. Common examples include LM2596 and XL6009. Applications include power supplies for electronic devices, battery-powered systems, and automotive and industrial electronics. Great! Let's break down how to design a voltage regulator circuit and how to choose the right one for your project. Before picking a regulator, define these key parameters. Input voltage, VIN. The voltage source you'll use, e.g. 12V from a battery. Output voltage, volt. The voltage your circuit needs, e.g. 5V for microcontrollers. Load current, IOUT. The current your circuit will draw, e.g. 500 mA for sensors and motors. And efficiency, which is important for battery-powered or heat-sensitive applications. If VIN is only slightly higher than VOUT and your circuit draws low current, use a linear regulator, which is simple and low noise. If VIN is much higher than VOUT, or if your circuit needs high efficiency, use a switching regulator, which offers better efficiency and generates less heat. For designing with a linear voltage regulator, take the example of the 7805 linear regulator for 5V output. The components needed include the 7805 regulator IC and two capacitors, e.g. 0.1 UF and 10 UF. The circuit involves connecting VIN to the input pin of the 7805, placing a 0.1 UF capacitor between input and ground to filter noise, connecting the output pin to your circuit, and placing a 10 UF capacitor between output and ground to stabilize the voltage. The pros include simplicity and low noise, while the cons are that it wastes power as heat and is inefficient for large voltage drops. Power dissipation can be calculated as VIN VOUT x IOUT. If VIN is 12V, VOUT is 5V, and IOUT is 1A, the power dissipation would be 12V, 5V, x 1A, 7W, which means you'll need a heatsink. For designing with a switching regulator, take the example of the LM2596 buck converter, which steps down voltage. The components needed include the LM2596 IC, an inductor, e.g. 33UH, a diode, e.g. 1N5822, and capacitors, e.g. 100 AUF. The circuit involves connecting VIN to the input pin of LM2596, placing a capacitor at the input to smooth voltage, connecting the output pin to your circuit, adding an inductor and diode between the output and ground, and placing another capacitor at the output for stability. The pros include high efficiency and the ability to handle large voltage drops, while the cons are that it is more complex and can introduce noise. Efficiency can be calculated as volt x IU, Vin x IN, x 100%. When selecting the right regulator, check the input voltage range to ensure the regulator can handle your maximum input voltage. Consider output voltage accuracy. Since some regulators offer adjustable outputs, ensure thermal management to handle the heat generated using a heatsink if needed. Look for quiescent current for battery applications, choosing one with low standby power consumption, and consider protection features like short circuit and thermal shutdown for protecting your circuit. Would you like a sample schematic or help simulating the circuit in software like LT-Spice, Proteus, or Tinkercad? I can also help calculate component values if you're designing from scratch. Let me know what you're working on.